Okay, we'll start inshallah. Welcome, Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to the Qur'an QA session that inshallah I will start by giving an overview on the first shared task on question answering over the Holy Qur'an. So we'll start with why we are doing that work. Of course, Qur'an is the main and major source of knowledge and legislation and teachings in Islam. And it is also a rich resource of knowledge for Muslims and non-Muslims who seek answers from it to their questions, whether the questions are out of curiosity or out of skepticism. And one of the tasks that are related to question answering and gaining a lot of attention recently by researchers is machine reading comprehension. Unfortunately, there is not much work on machine reading comprehension on the Holy Qur'an, and that's why we proposed the Qur'an QA 2022 shared task, aiming to encourage people to work on this problem, in particular machine reading comprehension, and in general question answering on the Holy Qur'an, inshallah. Qur'an QA is a shared task, as you know. It acts as a standard platform for researchers to jump into the problem easily, to make it easily for researchers to jump into the problem easily, inshallah, by providing formal task definition, labeled data sets, evaluation framework, and also a publication venue to describe their work. Of course, eventually, we hope that this line of research or research direction will produce real applications that will serve the Quran and also serve real users. And that's our actual objective of organizing such shared task. Here is how the task is formally defined. We are given a question in Modern Standard Arabic, MSA. We are given also a passage from the Quran, of course, a consecutive set of ayat from a specific surah. And we would like to build a system to extract answers from the passage. And the answer is defined as a span from the passage. So it's an extractive reading comprehension task. For this year, because it's the first time to propose this task, we define the task to return any answer. So if the question has multiple answers, the system that will provide any of them will be rewarded fully, of course, if the answer is complete. We also provided the QRCD dataset, the Quranic Reading Comprehension dataset, which was built on top of a dataset that we built 2 years ago called Ayatic. So Ayatic is a verse-based Qur'an QA dataset. Given some of the questions, we found all direct answers for these questions in the entire Qur'an. So we extended this work and we selected some of the questions. We extracted the answers from specific passages, and that's the QRCD dataset. Overall, we have about 1,100 question passage pairs, providing about 1.3K answers. We split the dataset into training 65%, development 10%, and test 25%, provided, of course, the training and dev for the participants, and we used the test set for final evaluation. After the test phase has started, we realized that some of the test questions overlap with existing data sets. So we thought that let's exclude them to have a fair comparison. So eventually we had 238 question passage pairs in the test set with about 300 question passage answer triplets. We perceived the problem as a ranking problem. So we use two types of evaluation measures. The first one is evaluating the top 5 ranked answers with a measure called partial reciprocal rank, which is an extension of the commonly used reciprocal rank measure. It just allows the partial matching of answers, because if we just use the exact match, that will be really harsh to the systems that can get partial answers. And of course, PRR also considers the ranking of the answers. That was the official measure in the task. We also used two other measures which only consider the top answer returned by the system. The first one is called exact match, which from the name, of course, just considers the exact full match of the answer with any of the gold answers, with the actual answers. And the other one was F1 which considers a partial matching. Those measures, they are more flexible and easier to interpret. That's why we provided them. Also, we report them for all the runs that are submitted. But PRR was the official measure because we were trying to give more chance for systems to find answers within the top 5. If you look at the three measures, you will see that EM is the most strict, then F1, then PRR. In terms of participation, since we announced at the beginning the start of the task, we got 30 registered teams, which is to us was beyond the expectation actually. Since the task is very narrowed in the domain and it's very new. Eventually, 21 institutes participated in the task. Many of them were collaborating, so actually they were 13 teams actually participated in the task. So we started with 30 registered, they got the training set, but eventually only 13 of them submitted runs. The submitted runs were actually 30. So for this set of numbers, I think that was really a very good start, and I personally consider that a big success to the first version of the shared task. This is the list of the participating teams. You can see from all over the world, from Asia, from Africa, from Europe. We actually have among the 21 institutes participating, we had about 8 that were non-Arab, which is really great for the first time. Overall, 40 team members composed these 13 teams. So for 40 students, academics, researchers actually participated in the task eventually. Based on the submitted papers and the system description of the submitted runs, we analyzed the descriptions, and we discovered mainly 3 trends in the methods. Of course, we will only focus on 3 here. There are more that you can find in the overview paper, but we will briefly discuss 3 of them today in this talk. We'll discuss the pre-training, we'll discuss fine-tuning, and we'll discuss the ensemble learning. For pre-training, almost all of the submitted runs used, of course, pre-trained language models. In the chart that you see, you'll see the distribution of them. As you see in the legend here, some of them were MSA only, some of them were used MSA plus classical Arabic, some used also dialectal Arabic, some used even multilingual pre-trained models. So you see here the distribution. Some of the key messages here. The pre-trained language models that were trained or that were pre-trained only on MSA were generally the best. As you see here in the chart, the runs here are sorted ascendingly in terms of performance, in terms of partial reciprocal rank. The ones that used pre-trained language models that natively used classical Arabic were all below the median, the median performance of the runs. And that's really interesting. And I would like to hear from the participants why why the performance was like that. it was surprising because you know that Qur'an is in classical Arabic. So a model, we would expect a model that is pre-trained on classical Arabic might give a boost to the performance, but that was not the case. Some also of the teams further pre-trained with domain classical Arabic text like fatwa websites or the Quran itself, but of course I think the performance was not that good due to the limited size of these resources. For fine-tuning, some of the teams used only the dataset that we provided, the label dataset that we provided. Actually, 10 runs used QRCD only. And these are the green ones here. You will see that 7 of them were almost below the median, so the performance was not that good. 3 of them were actually among the top 5. All of them came from the same team, and we believe that the reason is not that they used QRCD only, because they did some post-processing also, as we will hear today. So in general, using QRCD only was not helpful. So other teams tried to add or to use either existing labeled datasets for machine reading comprehension, or augmenting QRCD with more questions and answers. And actually adding or fine-tuning on QRCD in addition to other large machine reading comprehension datasets was really helpful. As you see here, the blue ones, almost most of them were actually among the top runs submitted in terms of performance. About augmenting QRCD with other sources, you'll see that there are actually 2 teams who did that. One added questions that are very similar to the questions in QRCD and answers, which are I think magenta here. Those green used Islamic QA websites. So that was not very helpful. I think augmenting QRCD was relatively helpful, and I would like to see in the future more of that. Maybe we can use them inshallah in our next versions. In terms of ensemble learning, I think 3 at least teams used a mix of trained models. 2 teams actually adopted ensemble of 2 or 3 different pre-trained BERT-based language models, all attained above the median, so it was relatively good. And all of them were MSA only. 3 runs of 1 team used what we call self-ensemble learning, which is using the same pre-trained model, but trained using different seats. And they were not, that was not very helpful. This is showing the performance of the runs, submitted runs, per question passage pair. So these runs are first sorted by their median median score performance, and for each one you see the distribution of the scores over all question passage pairs. So as you see, this box plot spans the whole range from 0 to 1. That means that the scores over all questions and passages were actually spanning the entire range of scores. The key message here that we can see clearly from that chart is that we have large variance of difficulty in our test set. Some of the questions were really easy. Systems got almost 1 for them. Some were really hard. Systems got very low scores. And I think this is good for a test set to have a large span of questions that are different in terms of difficulty. Just a quick pitfall here that I want to communicate to the participated teams and whoever is listening to us today, which is a key message in machine learning in general, and it was a message that or a lesson that we noticed from some of the participants. So the message here is that please never ever touch the test set. And touch means here that you, of course, your trained models should not, your models should not be trained on test set, and that's obvious. But even don't look at by your bare eyes at the test set, because that will be a big bias. So please avoid doing that, not only for this shared task, but in training your models in general. The test set should be completely unseen from you and from the models that you train, of course. Now to the maybe one of the most exciting moments in the talk. We are now announcing the ranking of the systems and the results. So we allocated actually 3 awards in the shared test to encourage the teams to participate and to do really hard work. Of course, it's just first version, so maybe the amounts are not that large, but I think they were a good incentive. We allocated $500 for the first ranked team, $350 for the second, and $250 for the third, with the condition that they will submit a paper, and the paper, of course, describing their work, and the paper gets accepted. So here are the 3 teams who got the awards. For the third rank, it is the GOF team, Ali Mostafa and Omar Mohamed from Helwan University. For the second rank, the QQA team, Basim Ahmed, Mu'taz Saad, and Esha Rifai from Al-Aqsa University, Islamic University of Gaza, and Jazan University. The third team, the first team actually was TCE team, Muhammad Al-Komi and Amani Sarhan from Tanta University. So congratulations to these teams. Actually, congratulations to all teams who participated, and especially for these 3 teams. Of course, we will be in touch, inshallah, very soon with you. This is the full team ranking for each team. What was the best run, best performing run, and the scores for all the 3 evaluation measures. You can see that the first team, TF200, got the actually the best performance, but it was not among the 3 winners because for some reason they withdrew their paper. So the paper eventually was not published or was not accepted. So actually the 3, that second, third, and fourth were the award winners. But the key note here that I want to emphasize is the score that we achieved by the best submitted run, which is 0.586, which is really quite high if we think about the first year of the test. If you just want to get an idea of what this score means, 0.5 of PRR means that you either, on average, you either get the half matched answer at rank 1 or full matched answer at rank 2. So within the first and second rank, you get either half matching or full matching, which is, I think, quite good as a start. Still, there is a big room of improvement, but I think it's a very good start. The TCE team also got the best EM score, although that was not the official measure, but the EM score, the exact match score at rank 1, it was 0.269. So almost let's say 0.3. So 30% of the time they got the first answer fully matching with the good answers, which is also quite good. You can see that 5 teams achieved better than 0.5 PRR, which is also very impressive. We also had a best paper award, which was not conditioned on the performance, but we actually had a specific criteria. We allocated $150 for this award. We had a criteria of 5 elements: novelty of methods, producing new sources, depth in analysis of results, clarity of writing, and clarity of presentation of methods and results. We'll keep the announcement of this award to the end of the session. So stay tuned, inshallah, to the end of this session. Now, what's next? for the next version of the shared task. I hope that there will be, inshallah, many versions. We started very simple this year with a simple task. We would like to propose more challenging tasks, inshallah, in the next version. Some of the ideas that we have, we might ask systems now to return all answers, not any answers. And sometimes also some of the questions might not have any answer in the passage. So the system should be able to say there is no answer instead of just giving any answer. We can also return answers from a specific surah or from the entire Quran. Of course, this is much more challenging, and that's actually was our main objective, is to find answers in the entire Quran. Ayatic and QRCD will help, especially Ayatic, because we found all the direct answers for the questions. Of course, we need to extend it with new questions and answers, inshallah, for the next version. We can also allow in some subtasks maybe to utilize external resources, maybe hadith or tafsir, in addition to the Quran itself. I would like, by the end, to thank very much the organizing team at Qatar University. Without them, we wouldn't have organized such tasks. Rana Manhas, my PhD student, who actually owns the idea and dreamed of this task for a long time. Now the dream came to reality. Also, Wathaq Mansour, the master student, and just graduated, by the way, and research assistant. Actually, Wathaq is looking for PhD opportunities. Wathaq was actually the technical guy behind this. Actually, he ran mostly the entire task in terms of technical work. I would also like to thank very much OSACT workshop for giving us the opportunity to organize such tasks. And finally, I would like to thank all participants. Actually, without them, we wouldn't have organized, or we wouldn't have had such day and such task. Without the participants, we wouldn't have Qur'an QA. So thank you very much, and I hope that you enjoyed working on this task and that you will continue working on this, whether within the shared task or in your own research. Thank you very much. I'm open to any questions. Any questions from the online participants? Yes, Amr, go ahead. I see Amr raising a hand. Go ahead, Amr.
Yeah, so hello, Dr. Tamer. Thank you very much for organizing this chair task. I have a question related to the dataset itself. So since it's based on Ayatic, and in the Ayatic paper, it was mentioned that actually questions are related to 11 topics, according to kind of classification of topics within the Quran. So I was wondering if you can actually provide such information as metadata for the questions, because it will help in like analyzing how the model performs in different topics and whether it's overfitting on a specific kind of topic, which might be related to specific kinds of questions. So
yeah, sure. We will be happy to do that. That's a very nice idea. That inshallah, hopefully this will help better informative analysis, of course. So inshallah, we'll consider that definitely. I hope that Rana is listening to me now and take a note of that, inshallah. Thank you.
I have one question. So I'm Wissam.
Who are you?
Wissam.
Oh, Wissam. Okay, from Obsidian. Okay, go ahead, Wissam.
Yeah. It's more like a discussion, not a discussion, like suggestion more than a question. I know that your group, Professor Tamer, works a lot on information retrieval. So I would like to see if you can like do a shared task on passage ranking, because I think like passage ranking and information retrieval is a bit lacking in Arabic specifically. So this is like a motivation.
Okay, another great suggestion. Thank you very much, Wissam. Yes, sure. I would love it much more than question answering. That's so IR is my task. Yeah.
If I can comment, so we already have a shared task on community question answering. We shared the data maybe in 2017. I think we shared more than 100K question answer pairs ranked pair relevance. Yeah,
I think in
sure.
semi-val, I think.
Yes,
Semi-val.
Question answering. Semi-val 2017.
Yeah, but it wasn't on Qur'an, I think. I remember it was from Islam Web question and answer.
We have one from Islam Web or something like this, and the other one from social forums like Qatar Living. Just
okay. Any other questions? I'm sorry that I ran out of time. I think. So
I have it says, sorry, Eric Atwell in Leeds University. To broaden this out, would it be possible to add parallel translations into English, since there are many English translations of the Quran, and to add questions and answers and the passage in English? So that would bring in many people who don't speak Arabic, who may want to enter the competition on the English version.
Sure, that's a third nice suggestion, but this is open to any participating teams. They can actually translate the questions. Questions are in MSA, so the translation will be quite good. We can, of course, provide manual translation, but at least any system can actually use maybe Google Translate and translate the questions in English or any other language.
But for the passage and the answer, you have to have a standard set to match against.
Yes, so you're talking about translation for questions only, right?
No, if I think that if you ran the same competition or a similar competition next year, then if you have not just the English questions, but also an agreed translation of the passage and an agreed translation of the answer or answers.
Okay, as an extended resource, you mean?
Yeah, then everybody would come up with the same comparable scores that way. If you just leave people translate it themselves, then they can come up with different translations of the same.
Sure. The only point here is that still the answers should be from Quran, not from the translation.
Yes.
So eventually, even if you will work on the translation, you will have to map it somehow to the actual passage in Arabic, in classical Arabic, in Quran text. Yeah, sure. Thank you very much. So, any other questions?
For the sake of time, we are 20 minutes behind schedule, so please timer speed up the following sessions.
Sure. Okay. Do you have any questions from your side, Hamdi? Okay. So if there is no questions at your side, then we will move on to the next speaker, which is Damith. Damith is here.
Yes, I am here.
Yeah, please go ahead and share your slides.
Yes, let me share my screen.
Since we are very tight in time, as you saw, that we have 10 minutes for the presentation, will be 8 for the actual presentation and 2 minutes for questions.
Yeah, I got it. Yes. So could you please stop sharing so that I can start sharing? Yeah, thank you. Okay, I think can you all see my screen?
Yes.
Yeah, thank you. Yeah, so thank you very much for giving this opportunity to present our work. So, and congratulations for the winning teams. It was a very nice competition, I think. The Quran question answering task, the short task itself was truly awesome. So we were team DTW at Quran Q&A short task, and the competitors were in the team were Damith Premasiri, that's myself, and Dr. Tharindu Ranasinghe, and Dr. Professor Ruslan Mitkov from University of Wolverhampton, UK, and also Dr. Wajdi from Hamad bin Khalifa University, Qatar. So it was a collaboration of work. For the introduction, as you all know, I would not go into much details of introductions because Dr. Tama has already explained the introduction and everything around that. But the machine reading comprehension is quite challenging, and also it is especially challenging for languages like Arabic, because Arabic is considered a low resource language compared to English. So it's quite challenging in that sense. And also we analyze the trends that people have followed throughout the years. And we were also going with the trend with the transformers in order to explore the capabilities of transformers in machine reading comprehension in Qur'an QA shared task. And also the main research questions that we try to address in our work was, do ensemble models provide better results in Qur'an question answering? And also, can other Arabic MRC resources such as SoQL could improve the Qur'an MRC task as well? So these are the main areas that we try to contribute from our work. And about the dataset, this slide, I think it is not needed to explain because Dr. Tamer has already explained it. We got the QRCD dataset, which was the main dataset. And also we used the SoQL dataset for the transfer learning. So the SoQL dataset has two main datasets. The very first one is Arabic Reading Comprehension dataset, ARCD, and also it contains the Arabic SCOT. So the SCOT dataset is widely used in English machine reading comprehension. So they have this Arabic SCOT, which is a translation of the original SCOT dataset, which we used in our work in this shared task as well. And also the neural network architecture. So the basic architecture is the transformer-based architecture. This is basically what we see in MRC task when we are using a transformer-based BERT architecture. So basically what it does is, so the transform models take an input of a single sequence that contains question and paragraph, and it is separated by the SEP token. And then the model architecture model introduces a start vector and an end vector. And the probability of each word being the start word is calculated and followed by a softmax over all the words. And then the highest probability of the starting word will be calculated, and that will be the start point of the span. So that's how the model works. And when we move into the methodology, we used pre-trained models for this MRC task. So these are the list of pre-trained modules that we used. Camel-Bird mix. So this mix is it's a modern standard Arabic and classical Arabic and dialectic Arabic as well. So it has all these three languages in training this model. And we used the Camel-Bird CA, that's the classical Arabic only. And we have used the multilingual BERT cased and multilingual based uncased, and array lectra generator, array lectra discriminator, and ARABERT v2. So these are the models that we evaluated. And also we used self-ensembling. Because the reason to use self-ensembling is like the transformer models are heavily biased to the random seed that is being initialized. So the results will be depend on the random seed. It could vary for the two runs, like it could generate two results or two reciprocal ranks for the final results. So we needed to make it regularized. So in order to do that, ensemble learning is kind of a standard way of doing that. So we used ensemble learning in our work too. And also we came across transfer learning, as I explained you in the beginning. We have used the SoQL dataset, which is we used the Arabic SCOT to transfer the learning to the QRCD dataset, because the QRCD dataset only had 710 annotated Q&A pairs. So we thought of, in order to optimize it, in order to make more use of the transformer architecture, it would be better to have more data, and more the more the data, more results will be, the better the results will be. So that's why we use the transfer learning. And these are kind of the benchmark that we got for the partial reciprocal rank. That was the official evaluating metric. So for the initial run, we did not use any transfer learning or any ensemble learning. So all these data, all these results were for the development dataset. For the development dataset, we achieved 0.549 maximum results for camel-bird mix. So as you can see, there were competitive other models such like camel-bird CA, which is the classical Arabic version of camel-bird, and also the eRock discriminator was very highly competitive too. And we got results for self-ensemble learning. As I explained, we used self-ensembling, but the results were not very much improving with self-ensembling. But on the other hand, we saw that the results are not going much lower as well. That means the results got stable, as in around this 0.52 mark. So it did not got much down, unlike when you're using a random seed like randomly. So the ensemble learning gave us a stable result. And also we used transfer learning with ensemble learning. So altogether that's self-ensembling. And we shortlisted 3 main models that we got better results for the development search. Those are eRock discriminator, camel-bird mix, and eRock V2. So we got 0.616 for development set using eRock discriminator, which was the better performer, and followed by camel-bird mix, which was 0.52. And moving on, results for the test set. So we evaluated the camel-bird mix with the different conditions. For example, with transfer learning and with ensemble learning, and with the, I'm sorry, this one is without transfer learning and with ensemble learning. So the second evaluation was with transfer learning and with ensemble learning, and the same configuration with eRock discriminator. As you can see here, the best performer that we got for the test set was our eRock discriminator, that was 0.495. So this was our best submission for the test set. And also, if you can see here, so the transfer learning clearly helps, because the same model performs way better than without transfer learning. So it really proves that one of our objectives in the beginning.
I'm sorry, Damith, you have 1 minute only.
Yes. Yeah. So as altogether, the conclusions were the eRock discriminator was the best performer of all the models as we evaluated, all the evaluated models actually. And also self-ensembling was stable the results, and also we showed that transfer learning does improve the MRC results of Qur'an. And also we have made available our code, software, and the Docker images and everything available for other researchers to work more on this task. So yeah, that's pretty much it for my presentation. I would like to hear any questions if you have.
Okay, thanks, Damith. Any questions for Damith, for the DTW team? I don't know, Amr, are you raising your hand?
No, sorry, I'm just clapping. So sorry, that's
okay,
just a clap.
So, okay, good. Okay, don't see any questions from the remote participants. Engineer Ham, did you have any at your side?
Let's proceed, Tamer.
Okay, so the next one, Esha Aftab, are you here? Esha?
Yes, I'm here. Okay, let me just turn on the
Please.
screen.
Yeah, go ahead and share the slide, please.
Okay. So I hope you can see the screen. Assalamu alaikum everyone,
Yes.
I'm Esha Aftab, and I am from Pakistan, Lahore. I'm currently a PhD scholar working with Dr. Kamran Malik. Can you still see? I'm sorry, there is an issue on my side. Can you still see the screen?
Yeah, I can see, but I hear also an echo.
Okay. Okay. Sorry, there is some issue from my side. I'll begin working on it. Okay, so here are the contents of my work today. I'll be covering the introduction and overview quickly, and then we'll move on to the methodology and model architecture, and we'll conclude with my results eventually. So here is the description of the task. Question answering is basically to provide a succinct answer to a meaningful question given over the context. And in this regard, there are some data sets that are worth mentioning. Most of them are in Arabic here because our question answer data set was in Arabic. However, I have mentioned Squad here being one of the most popular data sets, and the rest of them are in Arabic, out of which two mentioned here in are Qur'an based. And we also used these data sets during our work. Moving on to the neural models. I'm sorry, I'm just going a little bit quick due to the lack of time. So in the existing models, I have just mentioned those with the transfer learning, and those that are using the transfer learning techniques, because most of the teams have already used these or the variants of these models. So I'll not be discussing them in detail. The Qu'ran test has already been discussed by the organizers, that we had to pick the correct answer from the passage, and there could be many answers complying as possibly correct answer. And the goal was to select any one of them and rank them from 1 to 5. And here the table is listing down the count in each split. And so we had 1337 question answer passage pairs to work with in the original dataset that was provided to us. So in our methodology, we used BERT as a pre-trained language model, and then later on fine-tuned it for the specific task of question answering for QRCD. And we used two different pre-trained models. One was for the purely Arabic language corpus, and the next was a multilingual model, basically trained over 102 different languages. We used the regularization techniques like decouple rate decay and the data augmentation to avoid the overfitting and improve the general results. Here's the model architecture. So we started with the label training data, and then we augmented it with some additional data, and then the token embeddings are generated that are later fed into the BERT model, and the model is already pre-trained. So the output of the model is then passed through another layer to incorporate the loss of question answer error, to incorporate this error into the loss function of overall loss function. And then we fine-tuned this model, and eventually it resulted in the two vectors, giving the probability distribution of the start and end indices in the passage. So I will discuss data augmentation in a little bit detail, that how we came about it. The data augmentation was done using the annotated corpus of Arabic Al-Quran question and answer data set. And the data set originally has 22-24 question answer pairs, but they have released only 12-24. And the tuple is composed of many features, though I will not be discussing all of them right now. The ones that we used and that were of concern were those that coincided with QRC dataset. So here's this tuple, as you can see. There was this question ID, the question answer, just like QRCD, and the chapter number and the verses and the question particles. Question particle is basically the property that defines the kind of interrogation the question has in it. And there were no passages given, so we had to build some. Besides, there were some differences in the question answer style from QRCD, so we had to select some of the tuples using certain techniques. So for sampling and reforming data from this data set, we actually looked at this question particle property of this data set, and there were 43 unique particles identified. So a question could have been designated with multiple particles. So like this question, the 4 particles that are identified in it are highlighted here. So what we did was, as a first step of selection, that the questions that were containing Ashra or Fasr, they were mostly asking for the interpretation of the Quranic text. So we left them out. Yes. The overall nature of this data set was that it contained the questions in modern standard Arabic, while the answers were giving references of the verses from Quran, and there was also some MSA text in it. So we had to eliminate that text from the answers as well. So any question with the answer that does not mention or refer any verse from the Holy Quran is also eliminated. We wanted to keep this data set as close to as the one given to us, thinking that it might help more. Then answer cleaning was done, removing any plain text or MSA text from the verses that was appended before and after. And then we constructed the passages because they were missing from the original data set. So we downloaded the Quran text from the Tanzil project. And from there, for each tuple, the verses that were mentioned in the answer, we looked up those verses in the Quran. And then we selected 2 verses from the preceding and following context each, and then concatenated them with the original verses. In this way, we constructed the passage, and we identified the starting index of the answer, and stored the data set in the same way as the QRCD was. So we actually.
Sorry, Aisha, you have 1 minute.
Okay, so I'm just quickly moving on to the results. So here were the different settings under which we tested our data set. So this is the baseline model. As you can see, did not do well on the development data set, and so later on we not even on the training data. So we used fine tuning using birth-based Arabic as the pre-trained model, and we found it to be doing so well on the training data, but not much improvement in the development data. So some overfitting was there. To improve that, we applied the data augmentation and weight decay techniques. Here the run 2 and A and B are showing use of data augmentation. And we can see that the results were quite improved in R2A with 0.95 value of the training set and some improvement on the development set. Later, using both the data augmentation and the weight decay, our score was 0.96 on the training data, while it was 0.30 on the test data, which was also our best score amongst all the runs. And finally, we did, just for the testing purpose, we used the development data during the training in R5, as you can in the last one, just to see how further extension in training data pans out. However, the scores really didn't, they were not pushed to any new lengths. So we, so it highlights that initial data augmentation did all good that it could in the current setting, and it left no room for improvement with further data augmentation of the similar nature. So that was our score. And moving on to the next slide. So our key findings were that fine-tuning our pre-trained model specifically for the Arabic language resulted better than the one for the multilingual pre-trained model. And the regularization methods like data augmentation and weight decay enhanced the performance, but not too much. But they kept the model to some extent from overfitting. And for future, we expect to enhance the performance by making architectural level changes, and as well as we will try to increase data by rephrasing the questions by using techniques like back translation. And we also intend to use different activation functions and VLOS functions. So thank you very much. And I appreciate your efforts to all the organizers. Any questions are welcome.
Thanks, Aisha. Any questions for Aisha? Any questions at your side, G. Hamdi? Okay, thanks, Aisha. One more time. The next one is Ali Mustafa. Ali,
yes,
are you
Professor.
here?
Yeah, yes, Professor.
Okay. Can you please share your slides?
Yeah. My screen is clear now. Is my screen is clear now?
Yeah, but we don't see the slide. Yeah, please present full mode.
Yeah, okay.
Yeah, perfect.
Okay. Assalamu alaikum. Hello everyone. My name is Ali Mustafa. I recently graduated from faculty of computers and artificial intelligence, Haja University, and recently I started my master's degree in computer science at University of Windsor. Today we are talking about our paper entitled "Towards an Efficient Question Answering for the Holy Quran in the Arabic Language Using Deep Learning-Based Approach." Here's our agenda. Firstly, we will give motivation or why we use this approach. Secondly, we talking about the methods that we used. Thirdly, we are talking about results. Finally, we conclude. We will start by motivation. Arabic is a Semitic language spoken by about 250 million people in the Middle East and North Africa. Also, Arabic language is the official language for 26 countries and one of the 6 official languages of the United Nations. The Holy Quran, most of the Holy Quran is in CE, and Arabic has evolved over centuries, but now significantly CE is the basis of the medieval languages of Arab tribes. Also, more of the 1.8 billion Muslims around the world uses Quran as an essential component in their daily life. The Holy Quran consists of 114 chapters, approximately 6,000 verses. Most of the attention in the Arabic literature research actually is towards modern standard Arabic due to some limitations like resource availability compared to CA, especially for the Quran QA systems in the Holy Quran, because most of the questions in the Holy Quran is NMSA, because a lot of people in the Arabic regions uses MSA in their daily life. We will now we will go to the methods. Our pipeline is starting by fine-tuning our model on ARA-Tradikia QA datasets, then fine-tuning the same model in Arabic Squad on ARCD. Finally, we fine-tuning on the Quran QRCD dataset. We used ARA-Electra model as our base model here. ARA-Electra is an Electra-based model, but for Arabic language especially. The model is a bidirectional transformer encoder as BERT with 136 million parameter. ARA-Electra pre-training objective is place token detection, like they trying to insert some token, which is not, it's a fake, like as in the GAN paradigm, learning paradigm. First component is a fine-tuning on ARA-Tradikia, first component on pipeline. ARA-Tradikia is Arabic subset of the question answering dataset Tradikia QA. It includes 200 for question answer pairs, covers 11 to be different subjects in different diverse languages. TDIA KA has a significant benefit in the data, and that data is collected directly in each language without using neural machine translation as in Arabic Squad. ARA-Tradikia is composed of 5,000 training examples, with testing 900 examples with a total of 16,000 samples. Our model, which is ARA-Electra here, achieved an F1 score 85.7 and exact match 72.9. Second component, which is fine-tuning on Arabic Squad, the dataset obtained using a neural machine translation from the original Squad dataset, which is an English version. The translation was carried out using some translation method, which is Google Translate. The final distribution of the dataset is 84.3 questions on 10,000 paragraphs. Third dataset, which is ARCD, ARCD is not, it's like Dikia because it's produced not using neural machine translation. They retrieved top 1,000 viewed articles in Wikipedia in 2018 and then randomly sample it and try to make it as diverse as possible, including different topics. We go to the fine-tuning process on the squad and the RCD. We concatenated these two datasets, and then we fine-tuned the initial model, which is fine-tuned in a first dataset, which is Aratodekia. The same model was fine-tuned also for this combined datasets, wilding 49.7 questions, training set including 39,000. Here's the model RL-ECTRA obtained a F1 score of 70.5 and an exact match score of 36.4. Finally, fine-tuning these models into QRCD. Following the previous phases of fine-tuning the model on Aratodekia and Arabic Squad, ARCD, and ARCD, we acquired the model weights and then fine-tuned it again on QRCD to improve performance. The final model on the development set its development achieved 66.9 and 54.5 into this set. Why we follow this approach? We follow this approach because QRCD, a small sample size, is very small, so small, because also it's known that the deep learning models require a very large sample size, even if it's this model is pre-trained on a large corpus. So we use the cross transferability feature or transfer. We try to transfer knowledge from previous datasets of a question answering task to help the model retrieve better answers. Here we go to our results. We tried different models with different loss functions. We will talk about the point of loss functions later. First model was MARPERT version 2, using only fine-tuning it only on QRCD, using loss function cross entropy. It achieved BRR 50.4. Then we tried ARA-ELECTRA with QRCD. It achieved with cross entropy. Fine-tuned only in QRCD with cross entropy, it achieved 56.07. ARA-ELECTRA, we're using different loss function, which is focal loss label smoothing, achieved 57.6. Why did we use focal loss with label smoothing? As we know, in machine reading comprehension, it's a classification task to the indices. So if this indices include the question, it will be the class 1. Others will be negative. Let's imagine how will be the negative class here. So it's the machine reading comprehension serves from highly imbalanced datasets. Its datasets will be highly imbalanced or highly skewed. So our point of using focal loss smoothing to aid the problem of class imbalance. Unfortunately, we didn't have a lot of time to try these loss functions on the all three datasets. But we were talking about now ARA-ELECTRA, fine-tuning it Aratodekia, R-squared, ARCD, and QRCD with cross entropy achieved 66.9. ARA-ELECTRA using different loss function, focal loss achieved 61.2. But we only applied focal loss to the final model, which is QRCD, which is a big mistake by us. If we would see the effect actually of the focal loss, we should do it from the first phase, like using focal loss Aratodekia, R-squared, RCD, and QRCD, not only using get QRCD. Because of that, the performance of using focal loss is very low compared to cross entropy.
I saw you have 1 minute.
So Dr. Tamer, we need to
have
speed
1 minute.
up. We are super late. And it will be great if we postpone the session for any questions. We can post them on the chat, or we can communicate the author directly, because we are super late.
We have one talk that is missing, that we will skip. But we'll try to speed up.
Okay, thank you.
Okay. Final model was actually using dice loss also it's not achieved very impressive results. Here is a paragraph for different models. As we can see, fine-tuning QRCD achieved between 50 and 60. Fine-tuning QRCD improved performance, and the best model was the combination of the three or four different datasets. Official results here. This is official results from proceedings of LREC. Our team GF achieved 54.6 PRR, 23.9, and F1 52.5. Conclusion, we here used some approach for aiding the problem of small sample size and achieved 66.9 the development set and 45.5 on the test set. For feature works, we aim to experiment with different loss functions from early stages, not only in the final stages. Also, increasing the data set size may improve the model robustness using some augmentation and getting more data. Thank you. Any question?
Thank you very much, Ali. I don't see any questions on the chat, but if anyone has any question, you can post on the chat.
Okay, thank you.
Okay, thank you. The next one is Youssef. Youssef MELLAH, are you here? Youssef? Youssef? From the LREC2022 team? Yeah, okay. We don't hear you, Youssef. We see the slides, but we don't hear you. I still don't hear you. I don't know if others also had the same problem. I don't hear you.
Yes, Tamir, we don't hear anything.
Okay. So Youssef, please try to fix this problem at your side. We can see the slides, but we don't hear you.
Please, can you hear me now?
Yes.
I'm so sorry, I have a problem here. So can you hear me and see my slides?
So this is Ibtissam then, right?
Yes. I'm so sorry once again. Assalamu alaikum, esteemed audience. I am Ibtissam Touahri. I will present the contribution entitled Text-to-Text Transformer for further answers to questions from Qur'an on behalf of my team members. I would like at first to thank the Qur'an question answering shared task organizers for their efforts to make it successful. Really, thank you very much. Our presentation is outlined as follows. We describe the Qur'an question answering task, then we present our approach followed by the performed experiments and obtained results that will be analyzed afterwards. We conclude by giving some perspectives. Question answering is an interactive automatic process that belongs to Arabic natural language processing field. It provides the user with a solution that helps to achieve the exact answer of natural question. Quranic question answering helps to improve the time of Quran's knowledge acquirements. The Holy Quran is primary source for about 1.6 billion Muslims around the world. It is composed of 114 chapters, and its verses may overlap. To perform Quranic question answering, we have used MT5 model that achieved top results on many NLP tasks, among which question answering. The second reason for using MT5 is that it is based on encoder-decoder sequence to sequence, which is made it appropriate for the current shared task that we are performing for this competition. For this, we have formed the input sequence to our model as a question followed by its context, and namely the passage that contains the answer to the questions, then followed by a /s tag to denote its end. During pre-processing, we have removed stop words. We have also converted the JSON files given by the QRCD format to TSV file to be used to fine-tuning the MT5 model. The power here of transferred learning that we have based our tasks on comes from the pre-training a model on available and labeled datasets with self-supervision. After that, the model can be refined on smaller annotated datasets, which often gives good results better than training only on these labeled datasets. Hence, we fine-tuned the MT5 pre-trained model on the training sets of the QRCD datasets. We have used the original MT5 configuration in our system and considered three models, namely the base, large, and XL. They are characterized by the increase in parameters, which comes from the larger vocabulary used in MT5, since MT5 covers 101 languages. Here we give the obtained results that were evaluated by task organizers. As shown in tables, our base model achieves 0.98, 0.97, and 0.98, respectively in PRR, exact match, and F1 scored metrics, respectively. On the development set, which is a very good result. However, it decreases in the test sets, especially on the exact match metric. The obtained results may be due to many reasons, among which the ones related to the model itself that may be extractive as someone generative instead of being always extractive. Also, the problems related to the language, like its complexity and the lack of vocabulary of or synonyms to extend the given questions. To conclude, we recall that we have used MT5 language model and fine-tuned it using the training sets given training sets of QRCD datasets proposed by the Qu'ran question answering 2022 shared task. We have obtained good results on the dev set, but less on the test set. As further work, we intend to address the points raised by our system. The system may generate distant responses, especially when it comes to the names of prophets and messengers that may be confused with angels. Hence, the need for using named entities recognition. Our model also can be improved by addressing stemming, lemmatization or word roots, or even using synonyms to match the large sets of data and questions. Since QRCD is of limited size, yet imbalanced, we can use external Arabic data, mainly Qur'an and Tafsir, to pre-train MT5 from scratch. And doing after this fine-tuning, it will be interesting also to explore the text post-processing by addressing linguistic features. by this, I come to the end of my presentation. I would like to thank you very much for your attention.
Thank you very much, Ibtissam. You have a question on the chat from Amr. He says, just to make sure I got the idea correctly, have you generally fine-tuned the MT5 model to generate the right answer?
Please, can you repeat the question?
Okay, Amr, I think you can ask your question.
Yeah, sure. So thanks, Ibtissam. So my question is, you generally fine-tuned MT5 to generate the right answer. I mean, it's still a generative model in the end, so you aren't trying to do any restrictions on the output of the MT5, and yet it's still kind of magically understood that it needs to extract actually the output from the passage itself, but you haven't tried to constrain it, right? So it's still a generative model.
Yes, we, as I said, sometimes it is extractive since it will give a passage as it is, which means that the words in the same sequence as they was in the given answer. This is what I mean by extractive. And generation, sometimes it will generate much more words, even those that don't exist in the data set.
Yeah, thank you.
Thanks, Sam. The next one is Abdullah Saleh. Can you stop sharing it, Sam? Abdullah, are you here?
Abdullah is here, Dr. Tamer.
In person. Okay, very good. So go ahead.
I'm so sorry, I still have a problem to stop sharing. Just 1 minute.
Hello, everyone. Can you hear me in the in Zoom?
Yes.
And you can see the screen, right?
Yeah.
Well, Assalamu alaikum. Good afternoon, everyone. My name is Abdullah. I'm representing LK2022 team. We are PhD students at the University of Leeds, mainly supervised by Prof. Eric Atwell, Dr. Abdurrahman Al-Tahan, and Dr. Mohamed Ammar Al-Salka. Since we don't have much time, I'll go straight into the Qur'an QA dataset. We already know about the numbers of the QRCD question passage pairs. I would like to point out there are 114 questions that have more than one answer in training and development sets. And also there are 684 questions that were repeated in training and development sets. That proposes a challenge and an advantage as well. That they are duplicated questions for different passages, but it's also an advantage that the model does not memorize that this question would answer one given passage. We would have different passages that would answer one question. Also point out, there were no pre-treatment or pre-processing for the data set. Moving on to the model, we used simple transformers. Simple transformers is a library that is built on transformers architecture. The library provides many models. You have a classification model, you have named entity recognition, and also question and answering model. Also, the library simple transformers support many transformers-based models. We have Bert, Albert, Roberta, and others. And also this library, you can fine tune it. You can also adjust the hyperparameters if you like. And For the question answering model that we used, the model returns two lists. You have one list for the answers and one list for the probability score. So we needed to define a function to map the answers with the probability score. Now, the simple transformers needs specific format to feed it into the model. So this is the screenshot for the QRCD. So this is one example. So we needed to change that to meet the simple transformers requirement. So what we have done is that we have a key called context and also a key QAS. Context is the passage, obviously, and QAS is a list that has a dictionary of ID, surah, verses, question, and answers. We have done that by just modifying the function detect that was provided by the organizers. The three modes that we use are Arab BERT, Camel BERT, and Arabic BERT. You know by now. For the Arab BERT, we use a large model. For the Camel BERT, we use the classical Arabic, the base model. For the Arabic BERT, we use the large model. And we will speak on that in the original analysis part. For the experiments, so for the validation, we used obviously those three models, and we fine-tune it, and we also adjust the hyperparameters for the patch size, learning rate, and number of epochs. What is good about this library, you can adjust it using the methods they have for the model. As you can see it from the screenshot. And also, I would like to note that they have so many hyperparameters that you can adjust. You can also change the loss function as well. We didn't really do that. We don't have much time. So this is the results for the development set. So these are the top 3 results for each model that we used. And you can see the Arab BERT version 0.2 performed the best for the development set. Now, we didn't submit that in the Codalab. We've done that in the locally, unfortunately, but this is for the development set anyways. Now, we use the same hyperparameters for the test. For the test set, we also just used Arab BERT version 0.2. And this is the result that we have. It's close to the median, it's close to the average scores of the whole of all teams that they submitted to their test set. Now, moving on to the analysis part. So as for the model, we analyzed the development set results because we have the answers for those. For the test that the organizers have not published the answers. So for the model did not always return 5 answers. Sometimes it would return 4, 3, sometimes just 1 answer. Also, there were empty answers for 9 questions, and you would know these questions in our paper. We put the IDs in there. Now, the reason that the model could not produce an answer for these questions because it could not work it out for some reason. And we will see an example of that just a second. Also, part of the analysis that we have found is the words and phrases. Now, as you can see for the question, we highlighted with red, so you can see it, vigilant and lead. Now, these words and phrases were already mentioned in the passages. So we presume that the model could produce the correct answer because of the words and phrases that were already mentioned in the passage, and it should intelligent enough that the system would return the predicted answer, and it was. So the predicted answer actually was a sample, which is great. Now, if we don't have those phrases or words in the given passage with the same question, the model could not produce an answer. We don't have al-hulay or even synonyms of al-hulay in the passage. We don't have ijil also in the passage. We could argue that ijil means ilah in the tafsir, but it's also obviously probably the system could not intelligently know about the synonyms for ijil. So that's why the model could not predict an answer for now. Lastly, for the analysis part, potentially other correct answers, maybe. Now, this question was about متى يحل الإسلام دم الشخص. Now we have the gold answer, which is قاتلوا في سبيل الله الذين يقاتلونكم. However, in the predicted answer, we have فمن اعتدى عليكم فاعتدوا عليه بمثل ما اعتدى عليكم. We thought that could be another potential gold answer that could be added in the dataset. We looked at the tafsir and we also argued that in our paper if you'd like to read more about.
I'm not sure you have one. Okay, you are concluding. Thank you.
So for conclusion, we would like to thank the organizers for publishing the QRCD. It's a great addition to classical Arabic language as it is a low resource language. We used simple transformers library and obviously 3 Arabic language models. We found the Arabird version 0.2 was better. We believe that maybe it was better because it's a larger variant. It has Camelbird. We would like for Camelbird to publish a larger model for classical Arabic. Yeah, we can see it go here. And also we could have different parameters. We didn't really explore more about the hyperparameters that the model simple transformers have. That's our shortcoming. For the analysis, we just mentioned that the model could not always produce or predict an answer. We have also a problem with the non-matching words or phrases. Finally, we could have potential gold answers that could be added in the dataset. Thank you so much for listening. If you have any questions, I'm happy. Hopefully I am on time.
Yeah, thank you. No questions on the chat, so we'll switch to the next one. I think Nikhil, are you here? Nikhil? I think he didn't show up. So we'll continue with the Ishaq from the QA team. Ishaq, I think you are in person there.
So your presentation is not.
Yes. Yeah, that's me. Esha, that's me.
Presentation.
Maybe the PDF is saved.
Can you present from here? Can you present from here?
Sure.
Ishaq, are you there?
Yes. Assalamu alaikum wa rahmatullah.
Can
Can you hear me?
Please? Yeah, but we don't see your slides.
Sure. And can you see the slides clear?
No. We can. I don't see the slides.
Sharing.
Please share. Yeah, now we see it. Yeah,
Okay.
now we see it. Thank you.
Okay. Hello, everyone. My name is Esha Rifai, and today I will be presenting on behalf of my team, the QQA team with Dr. Basim Ahmed, Dr. Martez, and myself. Due to time, I'll be super quick. I will not be giving any background, jumping just directly to the methodology. We use the pre-trained model with the fine tuning. Specifically, we used 2 pre-trained models. These are the models. And then we use the merged version of these models. We did the fine tuning on the training data, and then we merged the data. We also did manual data augmentation by doing some paraphrasing of the training data set. We done just simple paraphrasing just to the questions, just to create a variety so that the model can learn from. The augmented data is available for anyone who would like to access them and maybe use them to find them useful. We submitted 3 different submissions using the 2 tuned model and a hybrid model. We used Collab Pro with a number of epochs up to 8 epochs. And then for the pre-processing, we applied just simple normalization. We did not do much of pre-processing. And for the results, here we got the best results with the R-Electra. And actually on the development, during the development test results, we got the best results on the hybrid model. And that would be all. And if you have any questions, you can email any of the authors. Thank you so much. And I would like just to take the opportunity to thank Professor Tamer and his team for all the effort. And I'm so happy to get this 2nd position, although we were aiming for the 1st place. And yeah, thank you all.
Thanks, Esha. I think you should have gotten the 1st because you were super fast in the presentation.
Okay, thank you.
Thank you. Okay, any questions for Esha? Okay, no questions. So the next one is Zam. I think you are here.
Yes, I am online. Let me just share my screen. Okay, so I have just shared my screen. Could you please confirm you can see it?
Yes.
Okay, thank you. So yeah, hello everyone. My name is Amr Kilic, and today I'm going to present our attempt in Qur'an QA 2020. And our paper is called Creating Better Faithful Data Splits for Low-Resourced Question Answering Scenarios. And it was done under the supervision of Dr. Walid Magdi at the University of Edinburgh. So first, what makes actually QRCD more special? If we compare it to Squad, which is a popular machine comprehension question answering dataset for English. So Squad has 100K questions for 23K unique paragraphs or passages, which implies that the average number of questions per passage is about 4.31. And if we look at QRCD, more specifically on the training split, we'll find that the questions are just 710 for 468 unique passages, which means that the average number of questions per passage is just 1.51. So clearly QRCD has smaller size, but also it has less number of questions per passage, which is a problem for large pre-trained models, because if they don't see different values or different questions for the same passage, maybe that's one more opportunity for them to overfit actually an answer for a specific passage. For the model fine-tuning, we didn't really use a special model, so we just fine-tuned different BERT models. So we feed the passage, the question, and just ask the BERT model to predict the start and end span from this passage. And more specifically, we tried 4 slight variations of the fine-tuning setup. So the first 2 are just fine-tuning different BERT models, which are Camel BERT pre-trained on classical Arabic and Camel BERT pre-trained on modern standard Arabic. And then we try to feed or augment the model with more information, like giving it information about named entities or stemming the text using Farasa before actually feeding it to the model. But in the end, we just went with vanilla fine-tuning Camel BERT classical Arabic without ensembling as our main model for this shared task. So once we fine-tuned the models, we had a problem that the PRR scores weren't actually stable. So we tried doing some error analysis. So the first part was to actually try to categorize the questions. So we used the interrogative articles like meta and aina and hala and so on as a proxy for the kind of reasoning actually that needs to be done by the model to answer such questions. And if we look at the distribution of the interrogative articles within the train and development datasets, we will find that actually articles like HAL and MASA are more represented in the development dataset than the other articles. And they also have good representation within the training dataset. And we also noticed that for such articles, there are questions having these articles achieve high PRR scores, which might indicate that there is a good generalization from the model, but actually we think that this wasn't really the case. So over here we are showing questions in the training dataset and another question in the development dataset that actually shares the same passage and shares the same answer. And if we look at the questions, we realize that they are actually paraphrases of each other. So if we say that the model is able to answer the question in the development datasets, maybe that's not actually generalization, and it's just generating this answer once it sees the passage, and it's not doing any kind of reasoning, which is a shame, I would say. So we decided to actually concatenate the training and development splits and try to resplit the data in a way that actually gives us splits that don't have such overlap, or we can say leakage, such that we can actually better understand how the models are working and comparing different architectures and models. So the process goes as follows. We first look at the passage for each question. If it's unique, then we see if the answer from this passage is found in any part of the training data. If that's the case, then we say there's yeah, sorry. I'll just go back once again. So first of all, if we see if the passage is unique or not. If not, then it's repeated passage, and we see if for this repeated passage it has actually a repeated answer. If that's the case, then this is the first bucket, which is more of a leakage because the passage is not unique, and also the answer is repeated with different questions or different triples. If the answer is unique, then we say this is still in domain because the passage is being used more and more, but the answer is actually unique, so there is no leakage. If the passage is unique, then this means that maybe the question will be harder. So we decided to also split it into two types. One where actually questions are, the question for this passage is also unique, and the other one which is a question that is being seen in the training data, but for different passages from this one. And if we look at the difficulty of generalization for these four new types of datasets, for the first one, we see that it has a repeated passage and also a repeated answer, which means that if the model just memorizes that this is the answer for this passage, it will be able actually to solve different variants of questions within this dataset. So yeah, this clearly doesn't really measure the generalization. For the second one, which has a unique passage, but a repeated question, we assume that maybe since the question is repeated, so possibly the answer will also be similar to other answers seen for other questions, and which implies there is still a possibility of memorization. For the third one, it's a unique passage and a unique question. So these are clearly unseen questions for passages that are unseen as well. So we can use them to test the true generalization of the model. And for the last type, it's a repeated passage, but a unique question, which means that the question is new to the model. So if the model actually memorized an answer for this repeated passage, then it will actually fail badly for such questions because it's a unique question, which implies most probably it's it needs completely different reasoning and it needs a completely different answer. So we would say this is the most challenging data set for the model. And for generating splits, we used random splits for the second and fourth data sets. We kept only one instance from triples having repeated passage answers pairs within the first data set. And we used actually the third one, which has unique answers and unique passages as a development set only, and we didn't really use it in training. And if we look at the PR scores achieved on the new development splits, so we change the model or fine-tune the model on a concatenation of the training splits from the 4 datasets, and then we evaluate on the development split of each dataset. So the scores on the development split of the first dataset is 0.8. For the second one, it's 0.5. Actually, it's the fourth, but I mean the second from the difficulty of generalization. For the third one, which has unique passages and unique questions, it's 0.4. And for the second one, or the hardest one, which uses unique passages, repeated passages, but unique questions, the PRR scores are the least, which implies that if the model actually is memorizing answers for this repeated questions, then it can't actually solve new questions that aren't seen in the training data, which implies it's actually memorizing and overfitting the data. And if we look at the evaluation of the different models on the third split, which is only used for development, we found that actually all the kind of attempts we were trying to improve the performance of the model weren't actually doing any kind of improvement. So we ended up just using the vanilla fine-tuning of Camel-BERT pre-trained on classical Arabic as our main model. And lastly, if we compare between the results on the hidden test set to the PR scores achieved on this third dataset, which we call out of domain and hard, we'll find that actually there is kind of a proximity between the scores. We can't really generalize and say that they are perfectly aligned, but at least we don't see much drop or much difference between the PR scores we get on the third dataset and the PR scores we get on the test set. So this kind of shows that by actually trying to avoid the leakage between the training and development datasets, we can actually achieve better understanding of how the models really behaves and don't get inflated scores on development sets that changes dramatically once we go to evaluate on the unseen test set. So for reflections and going further, we would say that maybe trying to minimize the leakage between training and development splits might be better for fairly comparing between different models and to actually get an understanding of how adding or changing hyperparameters or even architectures affects the results. We also say that we needed to use models pre-trained on modern standard Arabic, since it's crucial for questions. For example, in this question, هل أشار القرآن إلى نقص الأكسجين في المرتفعات? So clearly it uses the term oxygen or oxygen, which is not a term in classical Arabic. So for a model actually to be able to understand or to reason about such question, maybe it needs to have kind of an exposure to modern standard Arabic text. And we claim that if the way further is to create actually larger data sets that covers more topics or more question types, so maybe we can try to have more than one non-trivial question for each unique passage, such that the model doesn't just memorize an answer for each unique passage and then it's not doing much reasoning, but we acknowledge that this is actually easier said than done. And maybe when we have different passages, it's not actually trivial to find different questions that still make sense for each passage. And lastly, we think that it might be actually better to avoid questions that can have multiple interpretations, like متى يحل الإسلام دم الشخص, or when, I'm not sure if I can properly translate it, but when does kind of Islam approves to kill someone? And we think that actually such questions are not like factoid questions. They still have different interpretations, and given that actually the current models are just black boxes, so we can't really understand why the model is behaving in a specific way. So maybe it's actually better to avoid such questions and just focus on factoid questions that clearly have answers that will have less disagreement. So that's it for me. Thank you very much for listening, and I'll be happy to answer your questions.
Thank you very much, Amr, and very nice analysis of the data set. We have a question on the chat from Mohamed. It says, why do you think MSA pre-trained models performed worse?
So we didn't really try with different models. It was just Camel-BERT pre-trained on modern standard Arabic. Yeah, if I just get back.
Yes, as for us, we observed the opposite. Modern standard Arabic performed better for my case. That's why I'm asking. But I didn't try Camel-BERT. Do you hear me, Faris?
Yeah, I can hear you. Yeah. So, yeah, I'm sorry, I'm not really sure if I have like a clear answer for that. Maybe using different models kind of changes the results you get. I'm not sure about the model you have used, but I only used Camel-BERT. But yeah, I can give you different interpretations just based on my results. So I can't really say I had an intuition that classical Arabic model would perform better than the modern standard one. But yeah, that was the case for me. And yeah, I can see the point that for specific questions, using modern standard Arabic might be better. But yeah, it wasn't the case based on my fine-tuned models, which have lots of hyperparameters. So maybe yeah, I needed to fine-tune them better.
Okay, thanks, Sam. There is another question on the chat. You can, I think, read and reply in the chat from Professor Eric. Okay, thanks, Sam. Next, Iman, are you here?
Yes, I'm here.
Okay, go ahead, please.
Okay.
Can you stop sharing, please?
Yeah, sorry, I will. Sorry for that.
Okay. Sorry. Okay, assalamu alaikum everyone. We are STARS team, and today we will present our paper about building a system with transformer models and releasing a new dataset. This is our agenda for today. First thing about the data. There are the dataset we use for the Qur'an QA. This is the main and official dataset we use. It helps us for understanding the task and creating a similar dataset following the same structure. After searching for any open source dataset that can work fine for Qur'an QA, the only related dataset we found that the question answering compilation, AQQAC, is a collection of 1,224 question and answer, combining more dataset that can increase the dataset and get higher scores, but we still couldn't use it directly. Okay, this is for Arabic squad. This is the dataset with about 48,000 question on 10,000 paragraphs. The paragraphs are extracted from Wikipedia article. So this dataset isn't related to Qur'an QA, but we aimed to make the model deal with the Arabic question answer in general. After that, we expected the model can perform better when we apply the Qur'an QA. These are the challenges that we faced during building or developing our system. First thing, the limited question answer for QRCD. The data is small, which about 700 question. Most of them are repeated question for different passages from Quran verses. Second, the challenge and availability of open source dataset. And the third one, that with the previous two challenges, we decided to collect our own dataset to combine with the QRCD with the help of AQQAC dataset. The first, we plan to generate an automated dataset that enables us to create a large scale dataset. Creating it manually means consuming time with generating a small scale dataset. The challenges with the AQQAC dataset that the most of the answers aren't extracted from their specific passages. The passage and the answer are mixed with the Quran verses and tafsir, and there are answers with the same meaning but with different words that aren't found in the Quran. And also there are types of question like ما معنى كلمة مد لي من القرآن aren't related to the Quran QA task. So we couldn't solve all these issues. So we decided to do it manually by using the question of AQQAC dataset. Also, last one, about the Quran expert to add the accurate answer. Before answering any question from the Quranic passage manually, that requires knowing the tafsir and the meaning of the passage with related context events. So we have in our team a Quran scholar who added the passages and the answers for every question and created some similar question. These are data that we collect. We structured it like the original dataset and added multiple same question with other different passages. We used it for the first and second submission with about 600 questions. We collected more to be 700 questions and is used for the third submission. By using this data, the score in BRR increased by 10 in the BRR for the development evaluation. About the methodology, there are the four main components that we used for our approaches, the three approaches. First one, the masked language models that were the basic building blocks for our approaches. We haven't only made the use of existing Arabic pre-trained MLM like BERT, but also we created our Quranic MLM by fine-tuning our BERT on the Holy Quran verses only. Second step is the pre-processing, where we put together the two sequences of tokenization and encoding the tokens to be used for the fine-tuning. And for the fine-tuning, the MLM for our task, which is the third step. Finally, we tried using the ensemble of many fine-tuned QA models and take a vote of the best answer to achieve the better result. Okay. We fine-tuned the first approach. We fine-tuned our masked language models for Quran that we named Quran BERT. The first submitted, and we generated from the ensemble many trained models. Most of them were Quran BERT based model. Different combination of the data were used for training, and the weak learners, some were trained on QRCD only, and some mixed between QRCD data and our data, and another with a random portion of Arabic squad dataset, also with variation of training configuration. For the second submission, we have divided the competition dataset merged with our extracted our dataset into 8 folders instead of using normal bootstrapping, as we might get more dissimilar weak learners for better final ensemble model. Then the training of 8 transformer has been accomplished with the configuration based dataset. And the last one for this approach, we focused on measuring the effect of the size of the data on the performance. We worked on creating more examples during the last moment of the competition data lines. So we reached about 732 samples. And this combined with QRCD dataset to be 1,500 sample. Also, we did shuffle and used our BERT transformer-based version. This is about the last one. About the result. These are the results of the 3 different approaches on both development dataset. All 3 systems perform better than fine-tuning our BERT-based model with QRCD data. And these are the result of the test. We noticed that ensemble and the Quran QE aren't as effective as increasing the size of our data with fresh samples. And the reason of that we have only 1,500 Quran training samples in the best case scenario, which makes the split coming out of bootstrapping to be very similar. Also, the weak learner of the ensemble will be almost identical, especially given that the transformer are known to be extremely data intensive. And on the other hand, masked language models are known to be trained on a large corpus of the text. So training on the whole Quran or the verses about 6,000 verses are tiny in size compared to the enormous amount of the data that our BERT is trained on it, for example. Also, additionally, the question answering task model needs to learn the attention between the two different sequences of the passage, which is the non-Quranic sentence, unlike the single Quranic sentence in the masked language task. Conclusion, we proposed 3 different approaches. The best and the highest one was the expanding our data to achieve 0.528 MBRR. And the last one, and the second one, key folds ensemble, was 0.521. And the last one with the training BERT model in Quran. Then we use this pre-trained model for this specific task, Quran QA, and the BRR score of it was 0.502. The scores for all the 3 approaches are similar. For all 3 approaches, we developed the system with transformer models. Also, we proposed a new Arabic question answer dataset from the Holy Quran called AQ, about 732 question answers. In the future work, our data team aimed to increase the dataset. Also, we plan to cover all kinds of questions with answer, adding complex question and increasing the question with multiple answers. Also, we aim to improve the scores of the system. And the last one, we plan to make the system and our data available to the rich community. Thanks for listening. Do you have any question?
Thanks a lot, Iman. Any questions for Iman? I have a quick question, Iman, for the new data set, the 700 questions. How many of you extracted the answers, and did you actually compare the answer extracted if it's done by more than one person?
Yes, just one person of our team.
Oh, okay.
Okay, thank you.
Okay, thanks, Iman. Can you stop sharing, please? And Mohamed, next.
Hello.
Yes.
I will share the screen. 1 second. Do you see my screen?
Yes.
Okay. I'm going to present our work, Arabic language question answering over Holy Quran, using a post-processed ensemble of BERT-based models. This work was done in collaboration with my supervisors, Dr. Mostafa and Prof. Amani Sarhan. Long story short, it is an ensemble with a mixture of BERT experts, and we do some sort of post-processing to improve the results we achieve. As already introduced, the task for Quran QA, the shared task for Quran QA is extractive question answering task with which is evaluated as a ranking task, which means it's unlike the Squad 1.1 extractive question answering task. Following the mainstream for NLP, we use BERT for question answering by fine-tuning it as extractive question answering, as in attention is all you need paper. It works by adding 2 randomly initialized layers to predict the probabilities for start and end of the answer, the start and the end of the answer tokens, reducing the probabilities for them based on a softmax layer. And then we define the correctness score for an answer span, spanning from I to J as in equation 1. Jointly the scores from the beginning and the end of the answer span. The objective here is to maximize the likelihood for predicting one ground truth answer, which means this is the objective for Squad 1.1, and it is not optimized for our data set that expects a ranked list of answers. That's why during inference, we enumerate all possible potential or potential answer bands and take the top 20 of them based on their correctness score. I would explain why there are 20 answers, because they will undergo a process of post-processing. This is built for question answering from Attention is All You Need paper. To get more robust results, we employed an ensemble. We call it a span voting ensemble. I think some people has introduced similar ideas, which works by aggregating the correctness scores for every potential answer from a mixture of paired experts. Here we have a figure of 2 experts, 1 and 2, and the colors depict different answers bands predicted by them, and the height refers to their correctness score, their relative correctness score. As we can see, the span voting ensemble aggregates the blue one and the orange one, etc. And this one is assumed to be 0 to achieve a score 0 from the first expert. And we end up with a ranked list. That might be longer than 5 for sure, and this ensemble may work with any number of experts, or a mixture of paired experts. After that, we do a process of post-processing, which is designed to improve the BRR score we are achieving. First, it handles the subwords we may encounter due to the tokenization process that happens in BERT. We may end up with a span like this, which is incomplete. Noon here is an incomplete word. So we designed, so we implemented a simple rule to either drop or extend those incomplete words, as the example. And the most significant step in the post-processing is called, we call it redundancy elimination. It is designed for the BRR evaluation metric. If we think about the BRR metric, it only considers the kth plus 1 prediction if and only if the kth prediction makes a 0 overlap with all ground truth answers, which means it operates like a short circuit operator. When it finds any overlap at the kth prediction, it returns and gives the score. For that reason, if we repeat any word from the preceding answers, this makes the ranked list suboptimal for the BRR that's presented to the BRR evaluation process. After doing that kind of post-processing, we may end up with something we define as uninformative answers. An uninformative answer is an answer, it has 2 cases. The first case is an answer that's taken from the question. For example, this question and ما هي شجرة الزقوم, and the answer predicted by the model is a word that's taken from the question, which is completely uninformative. A second case is the whole answer of the model is a stop word, is an Arabic stop word, like ما, إذا, أو ليس. Those words, or as they are considered as whole answers, they cannot be representative to answer a question in QRCD. And after that, we may end up with a ranked list that might be longer than 5. We truncate this list, and it is the list is ranked or sorted based on the correctness score we defined in equation 1 at the beginning. Here is a comprehensive example for this process. I will show the process of redundancy elimination now. Considering a passage, a question and answer, and it's highlighted in green to show the answer span. Here, if we look at this example, we have 2 columns. On the right, these are the raw outputs before post-processing, and on the left, after post-processing. If we think about it, from the 2nd to the 10th place, we might see that the model is somehow confident around a certain answer span. That's why it's repeating it. The ranked list, the raw ranked list is repeated somehow. For that reason, we implemented a simple algorithm that scans the ranked list 1 by 1, and it eliminates any repeated words from the preceding answers. and we end up with somehow reducing all of those answers from 2 to 10 into exactly one answer. You may observe also from the colors after post processing that every word is shown or presented to the BRR metric only once after post processing. We can also see from the first answer here at the ranked list, which is a stop word. You can see that the model is giving a stop word as the first prediction, which is completely wrong, and it has to be rejected. And for that reason, we also implemented the idea of rejecting uninformative answers. And the BRR score raised for this example from a very low number into a much higher number. This step of redundancy elimination was the most significant step in the post processing. I think is the reason behind getting a good score, a good BRR score. Finally, our official results we achieved. Here I'm showing two runs of sample-based models. The first one is the raw outputs before post processing, and the second one is after post processing. We were able to achieve an increase of 2% in the BRR metric during the test phase. And most of it comes from the process of redundancy elimination. And this, you may find the source code here on GitHub. Also, feel free to reach out. The slides and the printout are also here on the slides. And are there any questions?
Thanks a lot, Mohamed. I really like the post-processing step. It's very well thought, I think. Though it's heuristic, but it works well. Any questions for Mohamed?
Yeah, can I ask a question from Mohamed? So
yes, sure. Can you state your name first, please?
Yes, Damith Premasiri. I'm Damith.
Okay.
Yeah, so Mohamed, so it's quite impressive work, congratulations. So I'm just wondering, you mentioned in the slide that the initial bird is not pre-trained. The objective was not really into question answering. That's why you took like 20 answers from the suggested answers. That's why you like take more answers and then you try to ensemble it and do sort of a post-processing. Can you please elaborate more? Why, like, what are the intuitions behind that, and something like that? Can you please elaborate more?
I think it was like a relaxed approach. What I mean is, instead of just presenting 5 answers to the ranked list, due to the post processing, as we can see here, almost as you can see here, those 15 answers after post processing has been presented as 5 answers to the BRR metric after post processing. What I mean is, we really need more than 5 because the models or those BERT-based models somehow are confident around a certain span, as you can see from the 2nd to the 10th place here, and all of those will be somehow reduced to one answer in the end. The other reason is we have tried, and the number 20 ended up with a ranked list that is somehow enough large for the BRR evaluation metric, which is 5. Because if you think about it, most of the models agree on some answer, on some specific answer span. So they will, 5 models won't be 100 answers. They will be less than that because of the aggregation process we defined in answer voting ensembles.
Dr. Tamer, Dr. Tamer, we are behind time, so we can take a quick question from Dr. Mostafa Jarrar. Then we end this session because you need the 5 minutes, as you told me, to announce the best.
Yeah, it's just 2 minutes that I need after Dr. Mostafa, inshallah. Yeah, go ahead, Dr. Mostafa.
Hi. Actually, I have a question, but it's not really also a question, and maybe you can answer me, Kamran. About question, I mean, this is very nice. It's going to lead to other, not only to Quran, but to other things. So question answering, and there is another task called intent detection. It seems to me if there is like labeling of the questions with intents, then it may improve. Then the problem becomes classification, then it's easier problem. Or at least if I want to form, I mean, I would like just to hear your opinion about intent detection, where you have many questions, several questions labeled with same intent, and then we decide or we classify question by intent. So the classifier is typically work with 90%, something like this in most cases, and then we decide.
So Dr. Mostafa, what do you mean? Yeah, what do you mean by intent here? Can you give examples?
Yeah, so sometimes you have maybe 100 questions, but all are different formulations of the same intent. Intent means
the actual meaning. The actual meaning, yani, of the question.
Intention. The intention.
Yani, and you mean same question but formed in many different forms.
Many different forms.
All of these will have the same intention or intent.
With the same intention. So if there is a task in LP called intent detection, which is just classification. It's just super easy task if we have a data set. And then, because if we know which intent, then it's easier.
But
like
if I understood correctly, the intention here is the actual meaning of the question. So there are no general classes. What are the general classes here? If we will do it as a
are the intents. So for example, I mean, I don't have example right now, but you can say, for example, what is Arkan al-Islam?
The topic. It can be topic.
No, this is
okay.
Not. Don't take it as a question. Take it as Arkan al-Islam, a label. But I can ask the same question.
على ماذا بني الإسلام?
In hundreds of ways.
So
first we classify by intention, and then we go to.
But we have unspecified the huge number of intentions, right?
Yeah, but if we talk about topic or categories, maybe we can do it that way. And within the topics of the whole Quran, there are categories. There are maybe a list of topics. Maybe we can categorize them this way. Yeah, I think we can do it. We can do it if I understood correctly. We can do it. But in our sorry.
Yeah. Thanks.
Thank you, Dr. Kamran.
Okay. Yeah. But just a quick comment. We don't have to my knowledge at least. Maybe Rana can correct me. We don't have in QRCD currently same question formed or stated in two different ways. Maybe of course they cover the same topic, of course, maybe Arkan Islam, as you said, or Ibadat, or whatever, or Qisas al-Anbiya, or something like that. But same question posed in two different ways. I think we don't have that, at least in the current version of QRCD. Thanks, Dr. Mostafa, anyway, for the comment, and we'll inshallah think about it.